Greetings, welcome, welcome. It's the greeting of the Organians from that Star Trek episode. I haven't posted anything in a while, and the reason was that this started becoming a not fun hobby. The last thing that I 3D printed with the Ender printer was this. And in the last video I was showing how even though it looked kind of alright, once I got it on, it didn't really print smoothly and it had a fair amount of wobble to it. So I was trying to redo that print with the Ender, and things just kept going from bad to worse, and so it was just like a litany of obscenities and cursing. And so I was like, that's not the way to have a hobby. So I just sort of threw up my hands, forget it. And then I thought about it for a while, and you know, I started off, I still don't know, jack squat about 3D printing, but I started off with the Vinci XYZ, and that's, it was alright for a few prints, but it's like one of those, I forget, they used to have a little toy oven, so that little kids could like pretend that they're using the oven to make things, and it worked, but it was just a little toy. That thing was really like that, and it also locked you into their particular spools of PLA material. It had a little sensor. It was like very dystopian, and then after a couple months the sensor broke, and so the thing was just a pile of garbage. And that was 220. So then someone said, well, why don't you try this Ender? And that was $200, and I got a lot of good prints. Well, I can't show you with this camera. I got a lot of good prints out of that, but it started getting worse and worse. And so after I threw up my hands, I mean, my first thought was, all right, I'm going to just tear this thing down to how it was when it first arrived. It took it took like an afternoon. It's supposed to only take an hour or two. I'm just going to unscrew everything and start over and see if I can figure out where the problems are. Because what was annoying is you get like 4 hours into a print and then it would screw up. And then I thought about it some more, and it's like, well, this Ender is, it's like 5, maybe 7-year-old tech at this point, and that's like a life age in technology now. So I wonder what's out there now. So I picked up, it's going to sound like an ad, but I mean, after the first print, I am really happy. After the first print, well, 2 prints. I mean, I did the test print. Here's the test print. They have this boat that I guess has become like a standard benchmark. I call it the Bodie McBoatface test. So that's what that guy is. And then I printed another one of these. And it wasn't perfect, but it was better. So to get back to it, I picked up the Cobra, Anycubic Cobra 2 Neo, $169. And I mean, I'm old enough to remember back when the top-end Texas Instruments calculators were like that much money. So it's sort of, first I thought about going for an $800,000 printer, and I said, screw it. I'm not that good at this yet. So I just thought I'll try to pick up the most recent low-end printer. The thing is fast. I mean, if people want, I'll do an actual review of it. But just like the things that are better, one, it has a magnetic bed, so you just put it there and boom, the plate that you're printing on sticks evenly because it's magnetized, and you don't have to worry about paper clips all around the thing. Secondly, it auto levels. You press a button and it goes boom, 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 and it's using either like a Hall effect or a Gauss meter to figure out how far it is from the magnetic bed. And that was one of the problems I had, is even when I had other things right, if I didn't have the bed level, then you just get a garbage print. So here you just press the button, takes it like 2 minutes, it levels it levels the bed for you. The third thing is it's fast. It's you know, the Ender is like someone just painting something in 3D. This thing, it's like the Star Trek replicator. You know, boom. It's I mean, that's exaggerating, but if this print on the Ender took 8.5 hours, it takes under 2 hours on the new Cobra. It's not. I didn't get every print right the first time. It's still, supposedly it all sticks to the bed fine, but you still should put down like some hairspray or something like that, because one of the prints just flew off. And part of that, I think, was I had it on a coffee table, and this thing is going so fast. Instead of, you know, like, it's going whoop, whoop, whoop. The whole coffee table starts shaking, and I think that kind of screwed the print up. So I put it on the ground, and I had one more where it still kind of came loose. But then I put down some hairspray, and it worked great. I don't know if this is interesting to people, but that's how you do that with that. And so then I got another one of these in under 2 hours, and so that's just, it like opens up a whole new world of prototyping when you can do something, you know, in an hour and a half that took a day before. So now the other reason I haven't done anything for a while was that you know, the pulse motor is not very good. It has a very low efficiency. You want a high efficiency, it has a low efficiency, and so that's not been as fun. And it also is just the number of different behaviors that come out of it is just astonishing. So I was kind of throwing up my hands there. You know, this is too much. But I think I will go along with it. I mean, one of the interesting things is just how much the behavior changes between the placement of your coil and your permanent magnet in all three axes. And so there's just a lot of different ways it behaves. But it's not very efficient in terms of a generator coil. And the reason why, so this video I'm just going to talk through like what I'm going to be looking at next. But the main reason I think that is the case is that you have a pulse. Boom, that's efficient. And then the rotor starts spinning, and you have your permanent magnet going past a coil of wire. Your permanent magnet's going past a coil of wire, and the coil is just sitting there in space. And so the permanent magnet, of course, generates electricity in that coil, and if that coil is connected back to, you know, your source or something, it's trying to feed back EMF back the other way, and it's slowing down with a physical slowing down of the rotor, just as if you had a shorted coil next to a magnet. You know, if the coil's just sitting there open, it doesn't care, but if it's shorted, then it presents itself as a drag because it's trying to do work. So in the same way, that coil is connected to something where the electricity that's produced can leave, and so it presents a drag as well. And because you're just pulsing and then it's sitting there for a long time, just going past the coil, that makes it less efficient. And I think a lot of, well, we'll get into that in a little bit. Okay, that's been a little bit, so let's get into it. So I think that a lot of this stuff that like Bini and Ron Cole and others were doing, I think a lot of it is addressing some of that. And so one example is with pulse motor. In a moment here we'll switch to like a different camera, and we can look at some of this on the internet and talk about it some more. But with an Adams type pulse motor, he has, 10-pound flywheel, attached 10-pound flywheel. And you first think about it, it's like, well, that makes no sense. But if you have this pulse, and instead of the thing being light as a feather, it has a way of putting the push into something that will have momentum, then it suddenly becomes a lot less counterintuitive. Yeah, if you can preserve that pulse in something with a lot of momentum, then that could mitigate your spin loss. So I mean, the example would be, something like the difference between a Tesla on a drag strip versus a locomotive. A locomotive, but once it gets going, it's going to be hard to stop. And so if you have something with some weight, once it gets going, the spin loss should have less of an effect. I mean, it's still there, but it's mitigated if you can get some of that rotational stuff to be in something that has momentum. I don't know. That's the only reason I can come up with for why you would want to put a 10-pound flywheel on an Adams type motor. So I don't want to make things too complicated with, like connecting this to here, and then, I'll put a big weight there or something, because a lot of times, since I don't know really what I'm doing with 3D printing, it don't turn out that well. But the idea I have is, if we go back to this guy, and I've actually thought about this a bit, is you could put a hole here, a hole there, a hole there, 6 of them, same size as a penny. See where I'm going with this, and bring it down, through the width of here, and so you fit about 6 or 8 pennies there, and you have about a penny roll. Now I did the calculations, and that will add about another 50%, pretty much all your weight, because this thing's light as a feather. Pretty much all your weight is coming from the permanent magnets. Putting in pennies as, like a penny roll, will add about another 50% of weight to the rotor. However, they're going to be on the outside, not in the inside. So it's not like you just made the whole rotor 50% heavier. You got the weight where it counts. And so it would be like, I don't know, making the rotor twice as heavy or 3 times as heavy, because it's out at the perimeter. So I figure that's worth taking a look at, especially now that I can do a print in an hour or 2 instead of a day or 2. So that's one thing. Now the second thing is I've kind of, I have looked more at the monopole setup with the 6 magnets, and I've gotten it better. I mean, I've gotten it to from like 20% to 30% or something, but I'm just sick of it. I mean, the image that came to mind was like when Homer got captured by Kang and Kodos. And he drops his pants. No! We've reached the limits of what rectal probing may tell us of your species. So, I've reached the limits of what I can do with that stinking monopole motor. So, one way to improve it, that I know will improve it, will be to go to bipolar commutation. And, it's not going to be well, it will be a pretty dramatic improvement. So that's one thing. So wait, go to a bipolar commutator. That doesn't address the spin loss. Although, I'm not 100% certain whether everything's going to behave the same in terms of, when you bring it closer, when you move it in this axis, when you move it in the other axis, whether that's all going to be the same as monopole. And since I know bipolar commutation is more efficient, it's like, okay, enough with that. Let's go to the more efficient one and see how that does. So I'd mentioned, you can see that 10-pound flywheel in the notes. And, the other thing, I think, just like with the window motor and the zero force motor that are radial flux, not axial flux, or maybe it's the other way around, but I think they're radial flux, not axial flux. I again think that's partially a response to the spin loss issue in pulse motors. There's another motor, and I'm going to see if I can dig this out and see if I remember it correctly. And can't remember the name of it, but it was back when Bini and other people were working on this in the 80s. But it's a pulse motor. I never know where these things are. And north, south, and then there's a piece of iron across it. And so there's magnetic flux between a north and a south. And once this thing is set up with bipolar commutation, and they said that's, you know, it's like 400% efficient or something like that. And once this thing's set up with bipolar commutation, you'll have a north-south 180 degrees opposite. And so you think about it, you have your magnet coming past, and it's generating per lens in the coil a force which is in opposition to the rotation. However, if there's a flux path going to an opposite polarity magnet on the other side, does it also go through to the other side and generate an attractive force while it's there? Does it communicate across the whole magnet then? I would think, you know, perhaps it does. Gosh. Sorry. So we'll take a look at and see if we can find that. But yeah, you know, that's starting to get into stuff with you know, shaping the magnetic flux path. And you know, there's that Thane Hines up in Canada has done some stuff with that, with transformers and things like that. That's one I'm going to kind of keep on the back burner. I mean, what you would do, again, never know where my hands are going to be. But, I mean, I could see like putting a groove in for a welding rod from one to here and then another one there. And then just put two welding rods in that are the same size so it's still balanced. And just run it, get rid of these other four, just run it with those two. And see if you run into the same issues. And if you don't, then that would be incredible. That's probably the last one I'm gonna, you know, I'll get the bipolar commutation going, look at adding weight. And the other one that I'll probably look at before that is the other way to get rid of spin loss is don't have the thing off so much. You know, the spin loss occurs when the motor's off. So in other words, if you go from 6 magnets to 8 magnets, your duty cycle here is probably about 50% when you look at the spacing there. When it's 4 magnets, it's on maybe 25% and off maybe 75%. It was a big improvement going to 6 magnets. Could you get away with 8 magnets? Could you get away with 10 magnets? I think at 8 magnets you'll probably be, you know, on maybe 2/3 of the time and off 1/3 of the time. And so that would help with torque, and there's less time for there to be spin loss. So that's definitely one to look at, is just have an 8-pole one with a little bit lesser spacing. Now the thing you'd have to be careful about there, well, there are two things. One is if your magnet, you know, if your electromagnet was way too big, it's going to be seeing too many magnets at once. So you'd need to have that size where it's not stepping on its toes that way. The other issue is because it's going to be on for 70% of the time, off for 30% of the time, you're trying to capture the inductive spike from the collapse of the magnetic field. Does it have time to collapse? And I don't think that'll be an issue, because you can essentially figure out, you can figure out how long it takes for the coil to collapse. It's the tau time of the coil, the inductance divided by the resistance. And just as there is, I don't know if they call it a tau time with capacitors, but the charge time, the RC the RC constant. So there's the equivalent of the RC constant with the magnetic field in a coil, and so you say need like 5 of those for this thing to collapse entirely. These coils are small enough and whatnot. I don't think it's going to be a problem. I mean, if anything, it would be nice if it was a problem, because that, I won't go into all that, but it shouldn't be an issue. You could even take it to its extreme here. And what if you had, if it'll show, just north, south, north, and they're like even touching each other. Now then the coil wouldn't have a chance to collapse, because I mean it would be on 99.9% of the time, and then kaboom, it sees the opposite voltage. But I just wonder what that would do. So that's way on the back burner. So those are the things I'm going to be working on here, and I think I'll get a lot of videos out pretty quickly. I think I can do a lot of work now really quickly. I don't know if I'll get a lot of videos out because the 3D printer is working well. Let's just take a look real quick at a few of these circuits, and then we'll wrap this one up, and then in the next video we'll have something spinning. We'll have something spinning bipolar, and then after that we're gonna put pennies in that thing and see if it makes it spin more better. Okay, let's look at circuits. So here is the, I guess in some circles, the rather famous Bini bipolar commutation circuit. And I really like this circuit because when I first, even got interested in this, I was thinking, well, wouldn't it be cool if you could drive the coil one way and then drive it another way and have it between a north and a south magnet? I bet that would work better. And I spent, I don't want to exaggerate, but probably weeks, like a week or two. I thought, oh, this will be easy. It's just one switch here and then one switch there. I did, to my credit, I did eventually, I'm so humble, I did eventually figure out that you needed a PNP and an NPN. But that's as far as I got, and I'm thankful to whatever the Bini forum was there, that I asked about it, and then someone just sent me this and said, oh, this is what you need. And so I kind of put it together, and it was really just a paint by numbers. I wasn't sure what any of these things, were doing. I know, I think pretty much what everything's doing now. But I just put everything in, plugged it all in, and it worked. And this was like, it's still probably the most complicated circuit I've ever built. Now that said, they did this back in the 80s, and nowadays you have these things. So I'm not going to try and focus it too much, but they're solid state relays. And so you have 1, 2, 3, 4, 5, 6 switches. And these switches here are needed to provide isolation. However, those solid state relays are opto-isolated. So you can get rid of this one and this one. You still have these 4, but this has 2 switches in it. It's a 2-channel solid state relay. So you have one of these for this and one of these for the other side. And that's all you need. Those are your 4 switches. And then you run it into an Arduino. So you see here's a Hall effect, and they use 2 Hall effects. Now one thing that I will say that I think is a bit of an improvement is if you use a ratiometric Hall effect, and I've talked about this in other videos, and you're running things through the Arduino, you can just let the output of the linear Hall effect tell you whether you're going past a north or a south pole magnet. So here, you have one south-facing Hall, or, well, I guess that's switch 1 and switch 2, but one Hall to detect south-facing magnets, one Hall to detect north-facing magnets, wherever the other Hall effect is. Yeah, Hall switch 2. You can get by with just one Hall effect once you run it into an Arduino. So that's what I'm going to build. You know, I've used that a lot now, but rebuild that. So here from this John Bedini's collection of free energy machines. If we go to, I think it was motor diagrams and lab notes, or ideas and motors. Ideas and motors. So, I mean, the first thing here, here's a monopole motor. Mass weight, flywheel of 3 pounds. And then we go down here, Adams type. And again, it's a monopole motor. Mass flywheel of 6 pounds. It's like, what are you doing? Why are you putting weight? That's going to make things worse. But again, I think it's because of the spin loss. And so you want, you know, you got that pulse, and then there's spin loss, spin loss, spin loss, and then pulse. So you want that pulse to be able to put itself into something that isn't feather light, or the spin loss will kill it. And so that's why, up until a point, imagine you get a bit better rotation paradoxically, or counterintuitively, not paradoxically, but counterintuitively, by adding some mass to the thing. And again, you know, there's these circuits, but it's so much easier with solid state relays now. There's something to do with bucking coils, but I guess there's not really enough there to understand what they did. Flux gate transformers. So here you can see they're starting to do stuff with flux paths. And then there's another one with flux paths. Let me see if I can find that one page. So here's another one where you have north, south. I mean, I don't know what they were doing with all these things really, but you can see that there is a connection now between here and here. Also, you know, like with Bedini's zero force motor, he actually had a big block of iron between the two coils. And everyone's like, what's that there? And it might have just been mass, but I don't think so. I think it was both mass and a flux path. So here you can see it more clearly. There's a connection between here and here, and between here and here, and then you have your coils. So here's actually a picture of this G-field generator. Here it's called a coal generator, but you can see, you know, because of the switching here, you have a pulse motor. And here's your coils. Now you have a south there and a north there. And so I'm guessing this be bipolar commutation again. And they're taking advantage of both ends of the coil, which is another thing to do. But you have this flux path there. Now the way I would think about it is that maybe when you have that, when you get this spin loss, now the spin loss can transfer over to this side. The spin loss from here can transfer over to this side, and so you don't get spin loss anymore. And that would be really cool. So eventually I have to have a go at this, but there's plenty more to do first, and I've talked at you long enough. I've got a new 3D printer, and if anyone cares to come along, I'll probably post a fair number of videos fairly quickly now and just start looking at all these different things. So sorry if it was all just kind of me yammering at you, but you know, for a while there I was kind of not having fun with this, but now I'm excited to go back to my hobby here. So thanks everyone, stay healthy, and talk to you again soon.